Good morning to all of you. For 2-3 minutes, please go through whatever we did so far. And if you have any doubts, questions, we can ask. Then we will start. So, are there any questions? If you are modeling it as axisymmetric body, yeah, you can use triangular elements for discretizing one cross section from these. So, I'll just, are there any other questions? I'll come back to this. So, are there any other questions? No, we have not. For which case are you saying? For the plane stress, plane strain problem, you saying? No? That is what, no? This term is that.
These both are external.
No, this I was saying that boundary traction on the element. So this is actually internal. Of course, when your entire problem when you are solving, this could also be on the boundary of the entire domain. There can be externally prescribed traction, but otherwise, when you are talking of the element, it is the internal only. So one question was about if the domain is axisymmetric. Although I have not discussed about axisymmetric problems, but suppose we have a cylindrical rod. I am just drawing the front view of that, and this is the axis of the cylinder. And maybe under certain boundary conditions you want to study, maybe it could be a say solid mechanics problem, or let us say heat conduction problem, and you have certain boundary conditions here and here. Basically along the this surface, curved surface and the ends, and temperature is, let us say, function of R and Z both. So what you can also do is you can actually use the so let us say this is my R direction and this is Z direction, and you want to formulate a problem, you can always use triangular elements and discretize the whole domain into a number of triangles. So exactly you can formulate in a similar fashion. Only thing you will find is that the integration domain is now in the cylindrical coordinate system. So it has to be, you will have to take the differential volume as 2 pi r dr into dz. So that you cover the basically circumference for axisymmetric case. So this is how you will handle this. You can have a triangular element, you can have a rectangular element. We are going to discuss subsequently isoparametric finite elements, so you can use those. The that comes from the actually convergence characteristics of these elements. So formally I have not discussed convergence, so I want to do that bit more mathematically, little bit rigorous way. So I have not yet done that, but see now what you are doing in case of a triangular element. So the next question was, how do we know that which element to use, whether to use a triangle or whether to use a rectangle? Again, if it is a triangle 3 noded or 6 noded, or a rectangle 4 noded, 8 noded, or so how to decide that? So that actually comes from when you want to solve the entire problem. You discretize the domain into a number of elements, and you will have to make sure that that number of elements is sufficient to give you the accurate solution. Usually, if the order of the order of interpolation within the element is lower, then its convergence would be slower. That means you need, for the given accuracy, you will have to use more number of elements. So for example, now if I use for this domain 3 noded triangular element, I will have to use large number of elements compared to if I use say a 6 noded triangular element. If I discretize the same domain into using 6 noded triangular elements, because in this case the order of interpolation, that is, no, you are using a higher degree polynomial for interpolating temperature within the element, so its convergence would be faster. So that means the of course, as long as you use sufficient number of elements, all elements will give you the accurate solution. So the only thing is computational cost would be more in one case and would be less in the other case, because the number of elements and overall degrees of freedom would be less if the element is based on higher degree interpolation. Then the other question was, in the last class solid mechanics problems, I had written the integral functional. So the second question was about I. So see, we had these terms of the integration over volume, and then we had written that as sigma transpose into epsilon and dv. Maybe dv I would have written as h into dx dy, and then we had body forces, so minus integration again over volume, and then we had written this as uv transpose into fbx fby and again dv. Then another term I had written was this integration over the contour, so that was I had written again as uv, and this was tnx tny, and then this is a contour integration. So these are the three terms I had written, and of course then sigma we wrote as c into epsilon, so this became epsilon transpose c into epsilon, and dv you can write h into dx dy. So those things we did. So see here, if you look at this is your strain energy, this is the potential of body forces, which are external forces acting on the body per unit volume, and then this term is the traction on the element. So suppose you have a domain, it can be any domain, and within the domain you have you are formulating the element level governing equation, let's say for a triangle. So what you are doing is you are isolating this, essentially like what we did in case of 1D. You are drawing the free body diagram of this. So in the free body diagram, what you will have is of course the body forces. So here you will have in x direction, in the y direction, so this is fbx and this is your fby, see this is x and y, and then on these boundaries, this tnx tny I said traction forces, that is force per unit area of the boundaries. So I said that here, let's say on this boundary we have the traction forces are say here distributed. This t and x is again force per unit area as I said, and this is t and y. So these are nothing but similarly here on this boundary you will have say t and x and t and y. I assume them to be positive, that means t and x t and y are positive along xy direction, so the potential is this. So here also we are assuming t and x t and y in that fashion, and these are nothing but your internal forces, because on this edge there would be forces exerted by the material here, on this edge there would be forces exerted by the material here, similarly on this edge there would be forces from this surrounding material, and that is nothing but we are accounting through the traction. So this is actually internal force vector, essentially you are accounting for the internal forces. But when you solve overall problems, because some boundaries you would have some externally distributed force might be prescribed on the boundaries, so you can also take care of that through basically this term. Otherwise, when the element is inside the domain, it is actually internal contribution to potential energy from the internal forces acting on the boundary of the element. Pardon? Yeah, actually it should be HDS, not because we are saying TNX, TNY force per unit area, so this should be HDS. I think I would have used HDS earlier. So, are there any other questions? This was clarification on whether we have taken care of internal forces acting on the element or not. So, this is actually to take care of the internal forces. So, are there any other questions? Okay, so then today and I had given you some 2 problems to solve, so I hope you have done those, and whatever I give you must do that. Maybe next class I'll give you some more problems, maybe bit more difficult ones. So the next one what I'm going to start is, so briefly about a 4-noded rectangular element formulated in physical coordinate space, and then switch over to natural coordinate space formulation. So first let me talk of this 4-noded rectangular element. Although as you see now that actually development of element level governing equations is essentially the same once we identify that what kind of interpolation we want to use. So this is in physical coordinate space, so as we discussed earlier that to ensure that we satisfy the inter-element continuity of primary variables, the element shape has to be rectangle. And if we are starting with a rectangle 4-noded, that's the minimum we can have. So these are the 4 corner nodes, say corner node 1, 2, 3 and 4, and in this case for ease of derivation of the element level governing equations, let me use this local coordinate system at first with origin at first node of the element. So let us say this is my capital X and this is my capital Y. Your global XY might be somewhere here. Okay. So then obviously the coordinates at this point with respect to these local element coordinate systems are going to be, this is 0, 0. The coordinates at this point is, let us say this edge length is Lx and Lxr. Let me use something different because two letters I don't want to use. So let me say A and this let me say B. So then the coordinates at this point in the local system xy is going capital X capital Y going to be 0, 0, A comma 0. The coordinates at this point would be A comma B. The coordinates at this point would be 0 comma B. And so these are the xy coordinates of these 4 current nodes. And if we are again let's say we want to develop this element level governing equation for a heat conduction problem. Of course, same thing you can do for the solid mechanics problem, plane stress, plane strain problems we discussed in the last class. So for this heat conduction problem, you will have say T1 as the value of temperature at node 1, that is the nodal degree of freedom. Here say T2, here it's T3, and at node 4 it is T4. So we have seen that for this problem, T is the primary variable, so obviously this should be degree of freedom at the nodes of the element, and so overall for the element we have 4 elemental degrees of freedom. So when we assume approximate solution, so we obviously should have 4 terms, so that we have corresponding to these T1, T2, T3, T4, 4 constants in the approximate solution, and we want to express this approximate solution in terms of, so you can also do in terms of small xy, but only thing is the derivation of shape functions would be little lengthier, I mean little more complex than if you do in the local coordinate system with origin at first node of the element. So you can assume this as say A0 plus A1x plus A2y and plus A3xy, because with 4 degrees of freedom per element you can have 4 terms in the approximate solution, and then this is what you should have a constant term, then linear in x, linear in y, and then this bilinear term x and y. So this is what you can have if you are formulating a 4-noded rectangular element. So this is your approximate solution, and what we do is first step in, see if it was actually we were trying to find out an approximate solution using either Betted residual or big form, then we would have directly solved for A0, A1, A2, A3. But in FE first we express this constant in terms of elemental degrees of freedom. So that finally the element level governing equations are in terms of values of the dependent variable or the unknown quantities. So if we solve for those, we directly get the physical variable which is the quantity of interest. So now we use the conditions of the nodal degrees of freedom. So here we know that T1 is the value of T at first node that is x equal to capital X equal to 0, capital Y equal to 0. So you get this as A0. So this is 1 because other terms are 0. Then if you look at T2, which is the value of T at node 2 where x is capital A and y is 0. So you get this as A0 plus A1 into small a, these two terms would be 0. So again here you can say that A1 would be T2 minus T1 because A0 is already T1 divided by A. Then T3 is nothing but, as you see, A0 plus A1 into A plus A2 into B plus A3 into A into B. And right now there are no A0, A1 are already known, but A2, A3 are unknowns. So we need one more equation which is actually your T4, and T4 is the value of T at this node. So that comes as A0 plus x is 0, so the first term goes to 0 plus we will have A2 into B. So as you see from this, A2 into B. So you can write that A2 is equal to T4 minus T1 divided by B. And once you have got this, then what you can do is you can now from this equation you can write the expression for A3. So if you look at the equation itself, T3 is equal to A0 is T1 we have written, and then A1 we have written as plus see this T2 minus T1 upon A into A, so you simply get T2 minus T1, and then A2 we have got as T4 minus T1 upon B, so it becomes T4 minus T1, and then A3 into A into B. So you will find, I think this T1 and this T1 gets cancelled, so you can write this as 1 T1 this side, so you have T1 plus T3 minus T4 minus T4, T2 minus T4 divided by A into B is equal to your A3. So these are all constants, A0 here, A1 here, A2 here and A3 here. Now if you put back this into the approximate solution, you can identify your shape functions. So that step is straightforward. Finally, using all of these, the interpolation of T finally can be written as, yes. So interpolation of T we can write in terms of shape functions here. Now see, we do not talk of here, like for the triangle we talked of area coordinates. In case of rectangle, we don't have that kind of a concept. That ratio of area of rectangle or something like that. You don't get in that format. So this T is here, say the shape functions N1 into T1. So let me write in terms of interpolation matrix. So N1, N2, N3, N4, and then into elemental degrees of freedom T1, T2, T3 and T4. Where of course we call this as H and this as D as usual. This is your H and this is your D. And in this H you have N1, N2, N3. So N1 you will find after you put these expressions for A0, A1, A2, A3 in this and then collect the coefficients of T1, T2, T3. You will find N1 would actually come out as, so there is a simple way of looking at this. Let me sketch the element shape here again. I don't want to go up and down again and again. So this is node 1, 2, 3, 4, 1, 2, 3, 4, capital X here and capital Y here. So you will find what is N1? N1 is corresponding to node 1 because this is getting multiplied with T1, which is the value of T at node 1. So N1 should actually be unity at node 1 and should be 0 at all 2, 3 and 4. So for that what we can do is we can write the equation of this line, and multiply them together. We actually get the shape function N1. Equation of this line is, if you look at x is equal to A. So I can say that x by A equal to unity R1 minus x by A equal to 0. So because x by A is going to vary from 0 to 1, so I can write that as 1 minus x by A into the equation of this line is similarly 1 minus y by b. So you will find if I just take the product of these two equations of line, that is equation of this line into equation of this line, I get this shape function actually n1, which satisfies the properties that n1 is unity at node 1. That means when I put x equal to capital X equal to 0, capital Y equal to 0, I get n1 is equal to 1. And if I put now the coordinates of either node 2 or 3 or 4, I get this as 0, because for node 2 capital X is equal to a, so the first term is 0, and for node 3 of course capital X is a, capital Y is b, so both of them are 0, and for node 4 capital Y is equal to b, so the second term is 0, therefore n1 is 0. So you will find that n1 is going to be 0 actually throughout this edge 2 to 3, 3 to 4. On this entire edge n1 would be 0, it is unity here, and of course it would be having some non-zero value from 1 to 2 or 1 to 4 and in between. So this is your n1, same way, and this you can actually get from if you substitute the values of a0, a1, a2, a3 in the expression for t, and then collect the coefficient of t1, so that would be exactly this, you can check that. So then similarly if I want to write now n2, shape function n2, it must be unity at node 2, 0 at 1, 4 and 3. So I can take the equation of this line and equation of this line. Equation of this line is x by a equal to basically 0. So we are taking only the left hand side x by a, and the equation of this line is 1 minus y by b equal to 0. So 1 minus y by b. So this becomes your n2. You will see that this is 0 at all the nodes other than 2. At node 2 capital X is a and y is 0, so it becomes unity, and you see at node 1 x is 0, so this is 0. At node 3 y equal to b, so therefore it is 0. At node 4 y equal to b, and therefore this is 0. So like that and this would be same as what procedure I already explained you. Same way you can write for n3, so n3 you will find it would be xy upon ab. That is going to be when you are writing this a function for this, it would be equation of this line into equation of this line, and so n4 would be then the equation of this line and this line. This line is 1 minus x by a into y by b. So these are the 4 shape functions. You can actually write directly for this rectangle in this case. They are also actually Lagrange interpolation functions. And once you have your shape functions, the rest of the derivation, development of the element level governing equations, and then the solution, the assembly and imposition of boundary condition solution, actually all those things remain same. So I am not going to discuss further on this. Once you have shape function, this interpolation, you can write the gradients del t by del x, del t by del y in terms of derivatives of n1, n2, n3, n4 with respect to x and y. Substitute in the integral functional of big form and get the element level governing equations. So except that now the integration would be little more involved, because you will find here that the derivatives of the derivative of, say for example n1 with respect to x is not now going to be constant, but it would be linear in y and so on, and similarly the derivative of n1 with respect to y would be linear in x. So now you no longer have B matrix which is constant, but it is function of x and y, so that has to be taken care in the integration. So except that rest of the things are actually same. But now here the same way you can go for the 8 noded rectangular element also. In the formulation derivation of the shape functions, everything would be similar. So but the drawback in this formulation is that no element has to be a rectangle in the physical coordinate space formulation, and that's a restriction, because quite often the real problems, the domains may not be actually regular. So you have to have for the total domain discretization, you need to have some general quadrilaterals, even sometimes with curved boundaries and so on. So then obviously these elements are actually restricted in use. So we go for what we discussed, the second approach of formulation in natural coordinate space. Natural coordinate space formulation. So I had mentioned to you about this. So here what we want to do is that the advantage here is that basically you can satisfy the continuity of primary variables across the elements for any arbitrary quadrilateral in the physical coordinate space. So then what you are doing in this, that no, in the physical coordinate space, although still the problem is has to belong to the physical coordinate space, all your energies, stresses, strains, you have to actually calculate in the physical coordinate space, but only for the purpose of interpolation we are mapping this domain into a domain in the natural coordinate space. So say that we have a rectangle, no, arbitrary quadrilateral in the physical coordinate space. So these are my coordinate direction x, y. First let us talk of a 4 noded quadrilateral element. So these are the nodes 1, 2, 3 and 4, because now I am not going to write the shape functions in terms of x and y. Again I am writing the coordinates of these nodes 1, 2, 3, 4 in terms of global coordinate system. Although I can always have a element coordinate system usually with no origin of the coordinate system at first node of the element, maybe the x axis is from first to second node and y axis is then perpendicular in the plane of this node 1, 2, 3, 4. So you can always have when you have direction dependent properties, you actually need the local element coordinate system, because usually the properties are given in terms of those, but for the timing we are just writing in terms of this. So this is here x1 y1, x2 y2, x3 y3 and x4 y4. So these are your coordinates. But then what you are doing, we want to map this to a space in the natural coordinate system. So there, because natural coordinates vary from -1 to +1. The idea here is, the basic idea is actually to satisfy the inter-element continuity of primary variables. And we have seen, we have argued out here that if we have a element, interpolation is shape of the element as rectangular, then we can satisfy the continuity of primary variables if they are degrees of freedom at the nodes of the element. So that is why we are converting this arbitrary quadrilateral into a actually rectangle, but then more specific it becomes a square. When we want to use the natural coordinates in both the direction, we want to use the same type of natural coordinates. So then here let us say you can use any notation. This is like x, y, you have xi and eta, you can use r and s. So there are in books different notations used. What we are saying, that this node is mapped to this particular node here. So this is node 1. You can other way also do, you can map this 1 here and this 2 here, then this 3 here and then this 4 here, that is also possible. But you have to maintain that sequence, and let's say anti-clockwise in this case. So this is node 1 in the natural coordinate space, node 2, node 3 and node 4. And since xi and eta, both of them are natural coordinates, they vary from -1 to +1. So the coordinates at this point are going to be -1, -1. The coordinates at this point are going to be +1, -1. Coordinates at this point 1 and 1, and coordinates at this point as -1, +1. So these are the natural coordinates of these 4 nodes in the natural coordinate space 1, 2, 3, 4. So this is as you see here, this is physical coordinate space. Physical coordinate space, and this is natural coordinate space. And this is, we call it as one-to-one mapping. So your mapping, you can see always if I have some point here xy, say a point P, this will correspond to a unique point in the natural coordinate space. So here I will have the corresponding point here in the natural coordinate space P with a certain coordinates xi and eta. So there is one-to-one mapping. So all the points, each point here in the physical coordinate space would be corresponding to a specific point in the natural coordinate space. Okay, so now once we understand this, that now we are mapping the physical coordinate space into natural coordinate space with xi and eta as coordinates, and the dimensions of the element here varying basically from -1 to +1. That means it's a square of side 2. We can now interpolate. So what we do now, the next is the interpolation. So obviously one is that we want to interpolate the unknown variables, dependent variables, for example temperature or displacements u and v, or any other quantity depending on the problem. But in addition, because we also need we need to know that if I know a point here, I need to find out what are the corresponding values of xi and eta or if I know a point here, the values of xi and eta, I also need to know what is the corresponding point in the physical coordinate space, that is xy values. So we will also have to write the relationship between xy and xi eta. So we call that also as the interpolation of geometry. So there are two things here. Now when you look at in terms of interpolation, so we have interpolation of dependent variables or sometimes these are referred to as field variables, and second is the interpolation of geometry. Geometry means in this case xy, or in case of 3D x, y and z. So interpolation of geometry in the physical coordinate space when you say geometry. So now when we write this relationship, we can have a one kind of a polynomial for dependent variables and another kind of a polynomial for geometry, same kind of a polynomial for both. In one case, maybe if you are having different polynomials for geometry and dependent variables, you can have higher degree polynomial for one case and a lower degree polynomial for the other case. So depending on that, we have three types of formulations. So one where we have if the order of interpolation of dependent variables and geometry is same, then we call then the formulation is referred to as isoparametric formulation. And this is actually most widely used formulation, although you can have higher degree polynomial approximation of geometry, lower degree polynomial approximation of field variables, that is known as superparametric formulation. And if the geometry interpolation is of lower order compared to field variables, then it is known as subparametric formulation. So there are two more, but this isoparametric formulation is most widely used one. So we will actually discuss more about this. We can always in a similar logic we can discuss the other ones. So now when you say isoparametric formulation, so what we are essentially saying that, let us say we consider the same heat conduction problem. So in case of isoparametric formulation, now we will have to interpolate both field variable, that is t, but this interpolation now we are going to write in the natural coordinate space. So t we will be writing say as a0. Now if it is the same, t is a primary variable, so must be degrees of freedom at each node, node 1, 2, 3 and 4. So there must be 4 terms in the approximate solution. So I can write this as a0 plus a1 xi plus a2 eta plus a3 xi eta. So again we are now using Pascal triangle, 1 xi eta, then xi square, xi eta and eta square. So we are basically taking these terms because we want to take 4 terms here. We are just taking these terms from this Pascal's triangle. So this is about the interpolation of field variable, in this case t, temperature, or u and v. There can be then 2 variables like in case of solid mechanics problem. In addition, we also have to interpolate now x and y. So see, only difference is that if you look at as far as t is concerned, the values of t at 1, 2, 3, 4 are here 1, 2, 3 and 4. They are unknown. Values of t1, t2, t3, t4 are unknown. Whereas because we know the geometry of the domain we are considering, so these x1, y1, x2, y2, x3, y3, x4, y4 are known coordinates of the nodes. So that is xy are known, whereas t1, t2, t3, t4 are unknown quantities, but we want to relate xy also with xi and eta. So we use in case of isoparametric formulation, we also write x is equal to say some b0 plus b1 xi plus b2 eta plus b3 xi eta. So we are using the same kind of polynomial for x also, x and y. So that is why we can refer to this formulation as isoparametric formulation. So y is equal to, let us say, another set of constant c0 plus c1 xi plus C2 eta plus C3 xi eta. And constants must be different, no, because x and no, x1 is it's not necessary, no, that x1, x2, x3, x4 are same as y1, y2, y3, y4. They in general would be different. So the relationship also individually these coefficients can be different. So therefore, no, we have to use different set of constants. Say A0, A1, A2, A3 for t, B0, B1, B2, B3 for x, and C0, C1, C2, C3 for eta. So this is the interpolation of geometry, and this is the interpolation of field variables. And they are of same order, that is we are using bilinear polynomial in xi and eta. So that is a constant term linear in xi, linear in eta, and bilinear term xi and eta. And that interpolation is same for both field variable and geometry, and that is why this is isoparametric formulation. The next step is again same, the way we did in the any finite element formulation, that we express these constant in terms of values of the variables at node points. So another difference is you will find that the as far as the physical coordinates are here, x1, y1, x2, y2, x3, y3, x4, y4, corresponding nodes in the natural coordinate space have coordinates -1, -1, 1, -1 and so on. But the values of dependent variable are here t1, t2, t3, t4, here also t1, t2, t3, t4. So what we are saying, the values of dependent variables, say here no, it is t1, here it is t2, here it is t3, here it is t4. So also in the natural coordinate space also we are saying that the temperature values are same. So we are saying that whatever point we have corresponding to in the physical coordinate space in general, say here there is a corresponding point here, the value of t here and the value of t here is same. So the physical coordinates, that is actually coordinates are different. In the physical coordinates they are the physical coordinates, in the natural coordinate space they are natural coordinates corresponding to different points, but the dependent variable values are taken same in the physical as well as the natural coordinate space. So then what we are saying, that value of t here is also t1, value of t here is t2, this is t3 and this is t4. So B is mapping only of the geometry. Now the variables we are saying that at a, whether the point in the physical coordinate space or the corresponding point in the natural coordinate space, the dependent variables values are same. So no scaling of dependent variables. It's only the change in the coordinates physical from physical space to natural coordinate space. So then what you do as usual, know that t is equal to t1 at first node. So you will see for the temperature t1 is equal to, at first node the coordinates are xi and eta as -1, -1. So you will get this as a0, -a1, -a2 and plus a3. That is t value of t at node 1 is t1, and at node 1 xi and eta are -1, -1. That is in the natural coordinate space, xi value is -1, eta value is -1. So you are writing this equation as a0 -a1 -a2 plus a3. Then t2 is the value of t at node 2, where xi is +1, eta is -1. So this would become a0 plus this is a1 plus a1, yes, and this will become -a2 and -a3 because your eta is -1. Then t3 is equal to xi and eta both are plus, so a0 plus a1 plus a2 plus a3. And then value of t at fourth node is xi and eta, xi is -1, eta is +1, so a0 -a1 plus a2 minus a3. So these are the equations for relationship between t1, t2, t3, t4 and the unknown constants a0, a1, a2, a3. Similar equations you can write for x and y also. So for example, if I write for x, so x1 is nothing but value of x coordinate, that is in the physical coordinate space, value of x at node 1. The corresponding xi and eta values are -1, -1. So you get b0 minus b1 minus b2 plus b3, because -1 into -1 this becomes plus. And then similarly x2 would be the value of x coordinate at node 2, the corresponding xi eta values are 1 and -1. So you get here, if you put the values here, so you get b0 plus b1 minus b2 and minus b3. Then x3 would be, so the form would be same. No, you see that these three terms are minus here, minus plus, the same logic here. And then similarly x3 is B0 plus B1 plus B2 plus B3. Similar fashion, now you can write your x4. So x4 is going to be B0 minus B1 plus B2 minus B3. So this is for your x. Same thing you will have for y. Now what we do, we solve say these equations for A0, A1, A2, A3 and then put back that in this expression, collect the coefficients of T1, T2, T3, T4, we get the shape functions. And you will find the form of shape functions because the structure of these equations, is the same. So in this case the shape functions are going to be finally same. So what you do, solve for these constants, put back in the interpolation which is given here, collect the coefficient of T1, T1, T2, T3, T4 or x1, x2, x3. You can finally write this interpolation for T, for example, as in terms of the way we have been doing earlier, n1, n2, n3, n4 into T1, T2, T3, T4. You can write in this finally in this form. After solving for A0, A1, A2, A3, putting back in the polynomial approximation, collecting the coefficient of T1, that is n1, coefficient of T2 is n2 and so on. And so same way you can also write for the geometry. So you can say x and y will be written as, and of course we do not combine the dependent and the geometric coordinates, because here these T1, T2, T3, T4 are unknowns, whereas in xy interpolation x1, y1, x2, y2, x3, y3, x4, y4 are known quantities, so we write them separately. So for this it would be like here there are 8 coordinates, so you can write this as say first x1, y1, then x2, y2, x3, y3, x4, y4. And then as you see x1 is going to be n1 x1 plus n2 x2 plus n3 x3 plus n4 x4. That relation is what? It is giving you x as a function of xi eta, y also as a function of xi eta. So x is n1 0, n2 0, n3 0 and then n4 0. So that it will give you x is equal to n1 x1 plus n2 x2 plus n3 x3 plus n4 x4. Same way for y will have 0, n1 0, n2 0, n3 0 and n4. So this is the interpolation of your dependent variable or field variable, and this is the interpolation of geometry. Now these n1, n2, the way I wrote actually for the rectangular element in the physical coordinate space, same way you can write, although the other step is, I already told that solve for all these constant in terms of corresponding values of the variables at the node points, put back, collect the coefficient, you get these shape functions. We can also write these shape functions directly, and keep in mind that these shape functions are going to be in terms of xi and eta. That means the interpolation functions are actually written directly, explicitly in the natural coordinate space. So I am again redrawing it here so that I can just refer this diagram. So this is xi and eta, this is node 1, this is node 2, this is node 3 and this is node 4. These shape functions n1, n2, n3, n4 again have the same property, that n1 is unity here, 0 at rest of the nodes. So see, you can write n1 again in a similar manner, that the equation of this line into equation of this line. So equation of this line is 1 minus xi, that is xi equal to actually 1, and since it varies from minus 1 to plus 1, you write it as 1 minus xi equal to 0. Equation of this line is 1 minus eta equal to 0. So you write product of these two, 1 minus xi into 1 minus eta. Now for this node, because xi and eta are minus 1, so if I put back these coordinates here, so it becomes 2 into 2, 4. But I want to make it unity, so I divide it by 4. So this is, then n1 becomes 1 by 4 into 1 minus xi into 1 minus eta. You would find that this is going to be 0 at other nodes. If for node 2 I will put actually xi equal to plus 1, so this term would be 0 and therefore this is 0 here. If I put the xi and eta as plus 1, again this is 0. If I put here say eta is equal to plus 1, because of this term it would be 0. So you find that n1 is unity here, 0 at that means actually it would be 0 along this entire edge, it would be 0 along this entire edge, unity here, and you will have some variation from 1 to 4 or 1 to 2 and within the element. So then same way you can write n2. Now for n2 it must be unity here and 0 at rest of the nodes, so you just take the equation of this line into equation of this line, which would be now if you see the equation of this line is xi equal to minus 1 or 1 plus xi equal to 0. So you will have 1 plus xi into the equation of this line remains same, 1 minus eta. Again, when you put the coordinates of this point, which is 1 and minus 1, this will come as 4, so be divided by 4, so that it is unity at node 2. So that when I put xi and eta as 1 minus 1, the interpolation of t directly gives me t equal to t2 for node 2. So same way you can write n3, so n3 will be 1 by 4, 1 plus xi into 1 plus eta, then that means that is the equation of this equation into equation of this line, and n4 then would be 1 by 4 now for this line, which is equation of this into this, so that is 1 minus xi into 1 plus eta. So these are the 4 shape functions. These same shape functions are going to be used here as well as here. Yeah, I wrote here, no, 1 by 4. Yeah, how this comes. So see, the property of these shape functions is, say for example, no, the question asked here is how we get 1 by 4 here. So we want to satisfy the property of the, of this n1, that it should be unity at the corresponding nodes. So n1 is corresponding to node 1, so it must be unity and 0 at rest other places. So of course, if you look at, if you put these coordinates are here plus 1, here the coordinates are minus 1 and 1. So if you put these coordinates at this point, at this point, at this point, here it is 0, but it must be unity at 1. But see, if I put that coordinates at this point, which are minus 1 and minus 1, this is 1 minus minus 1 will become 2 into 2, 4. So if I just evaluate the product of the two straight line equations, I get actually 4, the value of that expression. So I divide it by 4 to make it unity at node 1. And that is why we are dividing it by 4 for all the cases. There are 0 other remaining nodes, but to make it unity at the corresponding node, because when I evaluate just these two terms, it comes out as 4. So I divide it by 4 so that it becomes unity at the corresponding node. And this is to make sure that when we put in the interpolation for t, xi and eta as say minus 1, I must get that as t1, because that's nothing but the value of temperature at node 1. So if I don't divide it by 4, then I'll get it as 4 times t1, which is meaningless because we are saying that the value of t at node 1 is t1. So that's the purpose. And of course, if you are following this route of deriving these shape functions, that is solving for a0, a1, a2, a3 from this equation, and then putting back here in this, collecting the coefficient, that 1 by 4 would automatically come. Since here we are directly trying to derive, so we'll have to forcefully put this 1 by 4 to make it unity at the corresponding node. So this is how the derivation of these shape functions. Now another important thing here would be, I think some of you have class, so I will actually leave it early. So then next important thing is, now we have written the interpolation, and the next thing is, now we need the derivatives. So if you look at the either the weak form or the integral functional, you have the derivatives with respect to physical coordinate space. So again, right now what we did, we have only written the interpolation for t as well as the geometric coordinates x and y. But we need the relationship between derivatives in the physical coordinate space and the derivatives in the natural coordinate space. Why? Because see, it is very easy to differentiate t with respect to xi and eta, because if you look at this interpolation, t is expressed in terms of xi and eta. So we can explicitly get the derivatives of t with respect to xi and eta, but we want actually finally derivatives with respect to x and y, because finally we'll have to put that in the weak form or the integral functional. Same way, if you look at x and y also, they are written explicitly in terms of xi and eta. So we can also get derivatives of x and y with respect to xi and eta explicitly, because they are written in terms of these. So differentiation with respect to xi and eta is easier. But what we finally want is the derivatives with respect to x and y of the dependent variable, that is t. So if I take any function for that purpose, so let us say any function, let us consider, although finally we are going to take it as actually temperature. So let us consider a function, say f, and this is a function of xi and eta, because xi and eta, they are related to x and y. So you can also say that this is actually also no function of x and y, because no there is a relationship between xi and eta x and y. So if I have some function in xi and eta explicitly expressed in terms of xi and eta, I can always implicitly say that this is also function of x and y. So now if I want to write the derivatives of no f with respect to xi and eta, so I can say del f by del xi is equal to del f by del xi is equal to, now but I want to relate it with respect to in terms of derivatives with respect to x and y. So I can also say that derivative of f with respect to x and then the derivative of x with respect to xi, but since that xi would be also contained in y, so I will have to differentiate this with respect to y also. So I can say that this is also plus del f by del y into del y by del xi. So what I am doing is considering a function which is a function of xi and eta. There is a relationship between xi and eta and xy, so I can also say that it's a function of xy. So since we want to relate the derivatives with respect to two coordinate sets, so I am saying that let us say derivative of f with respect to xi is equal to del f by del x into del x by del xi plus del f by del y into del y by del xi. I can write this chain rule of differentiation on the right hand side. And see, maybe you can also say that why I am writing this relationship in this form itself. Why not directly del f by del x is equal to del f by del xi into del xi by del x plus del f by del y into del y by del xi. So no, del xi by del y. But the reason is, if you look at in this particular form, I have these available directly explicitly, because we have expressed x in terms of xi and eta, y in terms of xi and eta. So from this equation I can directly get from this relationship I can easily evaluate del x by del xi, del y by del xi, del x by del eta, del y by del eta. So they are easily available. We can evaluate them. So that is why we actually use this form. So now similarly, if I can write the derivative of f with respect to eta, so I can say del f by del eta is del f by del x into del x by del eta plus del f by del y into del y by del eta. See, we have to write these two terms, because once we are saying that f is expressed in terms of x and y, since the derivative is with respect to eta, x also has eta in it, y also has eta in it. So we take rate of change of f with respect to x and then rate of change of x with respect to eta plus rate of change of f with respect to y and rate of change of y with respect to eta. So that is how we are writing this. Now we can put this, if I actually take out the f function here and write the operator relationship, so I can say that del by del xi differential operators del by del eta operating on any function, in this case it is f. So I can write this is equal to, on the right hand side, again I am taking the right side the operators out. So this side I have del f by del x, del f by del y. So I am taking f out, so del by del x, del by del y. So this is what you will have. So this side I am just only taking out f, that's it. So del f by del xi, del f by del eta. So then now see what you are left with is here del x by del xi and del y by del xi, del x by del eta and del y by del eta. And this relationship what we have here, this is actually known as Jacobian matrix. So I am going to stop here because other students have class here, so we will continue in the next class. So this is where I stop. We will continue in the next class. If you have any doubts and questions, you can ask outside, and I will continue from here. So I will again next class first discuss little more about this and then we will continue.